Okay, it's Tuesday. We're back here, Physics 1151. We're starting a new chapter today, chapter 28, and it's the introduction to DC circuits. So if you look at all of these things right here, we've got household wiring, you have your cell phone, you have your laptop, you have a car. What these have in common is that they all have circuits built into them, and we'll see that all a circuit is it's a typically, well, always, it's a source of energy connected by wires and or traces on a PC board to components or devices that use this energy for a specific purpose. For example, to run our cell phone or our laptop or our car, or in our house here. So we need to develop a little bit of a basic understanding of circuits. And we're going to start simple, and then we're going to progressively add a little bit of complexity. So I hope that you find this chapter to be a little more intuitive once we get the techniques down. It's integrating a lot of those abstract concepts like potential difference and electric field and resistivity and all these other things that we developed in the previous chapter. Now we're combining them into something that we can see in our everyday lives. So we're going to get started today just with, a brief introduction to what a circuit is, how to draw and interpret a circuit diagram. Again, we're going to start basic and progressively add complexity in coming lectures. And then we're going to get our first taste at analyzing a basic circuit. Homework 10, haven't made it up yet. You're probably thinking about homework 9 right now, but I've got a tentative due date of Sunday the 11th on this. It will not be any sooner than that. There's a possibility that I may push it back a day or two. I think we're all getting behind right now in the semester. And the required reading for this particular set of lecture notes is 28.1 and 28.2 of the text. Here are the learning objectives of this set of lecture notes, which will mean more after we go through this. So in the chapter, we're going to start off with basic DC circuits, okay? In DC, you may have seen this. If you look on the power supply for your laptop or other things, you might say 5 volts DC or 12 volts DC on your car battery. DC is the acronym for direct current. What direct current means is it's just a circuit where the current only flows in a single direction and its magnitude doesn't change with time. In other words, it's a constant. And some examples of this are most of the electronics in your car runs off your 12 volt car battery. It's 12 volt DC. What it does not include is the wiring that comes into your home. This is what's called alternating current, or AC. And that's what's coming into your home, and that's what is connected to the boxes, the receptacles in your home, is that 120 volts AC comes out of your breaker box, and it gets divvied up amongst all the devices that use it. So this is what's called AC current, and this is what's called DC. AC is slightly more complicated, so we're going to defer it for a couple chapters, and we're just going to start with DC. DC also works your cell phone, your laptop. You plug the laptop into the wall or you charge your cell phone, and you notice it has that adapter, that power supply, right, that you plug into the wall. That power supply converts AC, alternating current, at 120 volts to DC current at 5 volts for most of your digital electronics. And so that power supply converts AC to DC. So in this chapter, we're going to start off a little simpler with circuits that use DC, or direct current, and we'll get to AC later. By the way, yes, the band AC/DC does come from alternating current and direct current. Okay, so if you want to call the band by its proper name, it would be alternating current, direct current. But anyway, that's a pretty lame joke. So to start off, before we start analyzing circuits, we need to introduce this concept of a circuit diagram. And the best way to do this is through an example. Okay, so here we have some wires in a circuit, and you have a battery, and you have the battery supplying the energy, and then you have a resistor, which this could be anything. This could be something, a tungsten light bulb or anything, but it's using the energy from the battery. And then we have this capacitor here, and the capacitors are usually used in circuits. We discussed storing energy in the previous chapter, but they're also used to filter out noise and for other applications. So you have a resistor, and you have a capacitor, and you have a battery, and they're all connected in wires, by wires. And if you look at the wiring, this is what's called a parallel circuit. And by parallel, it means that one end of the resistor and one end of the capacitor are both connected to the positive terminal of the battery. They're both connected to the same point. And the other end of the capacitor and the other end of the resistor are both connected to the negative terminal of the battery. So what parallel wiring means is that all of the components in the circuit, in this case just the resistor and the capacitor, have their two wires connected to the same point. They all have one wire connected to the negative terminal. They all have another wire connected to the positive. And this is what's called parallel wiring. And the different boxes in your home, the different wall outlets are wired in parallel. If we go back here and you look, each of these circuits in the home are wired in parallel. In other words, they both have a connection to neutral, they both have a connection to hot, and they all have a connection to neutral, they all have a connection to hot, and they all have a third connection to ground. So don't worry about hot, neutral, and ground right now. Just parallel means that they all of the components have one connection to the same place and another connection to the same place. And that's what's called parallel wiring. Now, it's not very convenient to keep this in terms of the wiring diagram when we're trying to analyze this circuit or design a circuit. So in other words, what we're going to be doing in this chapter is we're going to want to calculate the potential differences across all the components and the currents through the components. And to do that, it's usually much easier to first draw this wiring or this circuit using what's called a circuit diagram. And this is a little bit weird at first, but it's pretty easy once we do it a few times. So to analyze a circuit, we draw the circuit diagram here. And what we have to get used to is we have to learn the symbols used to express each component. Okay, so here's a battery. A battery is drawn as a series of larger and smaller lines. Okay, they're parallel lines. And the largest line right here corresponds to the positive terminal of the battery, and the smallest line corresponds to the negative. Okay, don't ask me why they use 4 lines and not 2. But often they use 4, sometimes they use 2, just to mess with you. But the largest line corresponds to the positive, the smallest line corresponds to the negative. And so we're going to draw our battery as these 4 lines. Okay, the battery, the top terminal of the battery is connected to the top terminal of the resistor using a wire. And we draw the wires as straight lines, okay? And we typically draw them as using linear instead of, curves, but it doesn't matter. So we connect the resistor, and the resistor is denoted by all of these squiggly lines. There's the symbol for the resistor in a circuit diagram. Positive terminal is connected to the resistor by a wire. So there's the top connection, okay? Bottom connection of the battery is connected to the resistor by a wire, and so we draw a wire, which is a straight line, going from the negative terminal to the other end of the resistor. Okay? So now we've drawn our battery source, and we've drawn our resistor. Now these are wired in parallel, right? Because the top of the battery, the positive terminal, is also connected to one terminal of the capacitor. So we draw the capacitor, the wire going from the top terminal directly to this lead of the capacitor, and the capacitor is just two lines that are the same length. There's the symbol for the capacitor. And then we draw the negative terminal of the battery getting connected to the other terminal of the capacitor. And so this is what's called a wiring diagram. It's a representation using symbols and lines of the actual circuit up here. Okay, so we're not using too many components in this course, so I think you'll get used to these symbols pretty quickly. Okay, and you can see that this picture denotes the fact that the resistor and the capacitor are both connected in parallel to the battery. They both have one wire connected to the top, and the positive terminal, and they both have the other side connected to the negative terminal. So this is parallel wiring. Okay, so this is the circuit diagram for the circuit whose actual wiring is shown here. And you should be able to, and that's one of our learning objectives, you should be able to take the wiring picture and you should be able to draw a diagram of a circuit. Conversely, if you're in lab, you're doing all this stuff virtually this semester, unfortunately, but if you were in lab or at home and you saw this circuit diagram, you should know how to wire the components. Okay, so this is going back and forth. So let's do another example here. So draw the circuit diagram corresponding to this actual circuit. Okay, so you have a 9-volt battery, and the positive terminal is connected to two resistors, a 50 ohm resistor and a 100 ohm resistor, and these are in series. Series means one after the other. So you have a wire going to one end of the 50 ohm resistor, the other end goes to this one, and then it goes back to the negative terminal of the battery. And so series means you just daisy chain the components one after the other. So the 50 ohm and the 100 ohm resistor are wired in series, and this forms one loop. Okay. Now in parallel with that loop is another resistor whose magnitude is 75 ohms. And you can tell they're in parallel because the positive terminal is connected to one end of the 75, the other end of the 75 ohm comes back to the negative. And so both loops have the same starting and ending points, namely the terminals of the battery. And so these two circuits are connected in parallel. So how do we draw this? Okay, well, remember battery is the 4 lines, and so we can start here. And the battery is connected by wires, which are straight lines. And the first loop involves the wires going to the 50 ohm resistor, and then to the 100 ohm resistor, and then coming back to the negative terminal of the battery. And so that's the first loop. The second loop, which is in parallel, involves the plus 9-volt terminal getting connected by a wire to the 75 ohm. And so if you go through here, it's connected to the top terminal there, and then the other terminal of the 75, the other lead, getting connected to negative 9 volts. Okay, and so now we have drawn a circuit diagram which corresponds to this circuit right here. And I'm going to give you another example in the homework, and there's a few more examples in the text, but really take time to learn this, not only for this class, but this ties together what you see when you're looking at a circuit. You see wires and you see components with the circuit diagram that's used to represent it. And you should be able to go back and forth between these two pictures. So if you look at this here, we're going to get into the details of how to analyze a circuit like this shortly. But if you look, there's 2 loops for the current to flow. The current can flow through the left loop or the current can flow through the right loop. Okay, and if you look, here's a junction, here comes the current. It can choose one of two paths. It can either curve right here at the junction and go through these two resistors, or it can go straight and go through the 75 ohm, and then they both merge and they come back here, and the sum of the currents goes back to the negative terminal. So we'll get into analyzing this in a minute, but this is the circuit diagram for this circuit. So let's do another example here. The question is, which of these diagrams represent the same circuit? In other words, which ones are actually the same physical circuit but drawn just a little differently? Okay, so let's look at this. This left circuit is just what you had back here. You have a battery, and the battery is connected to a resistor and to a capacitor, and they're in parallel. Okay, so look here. That's a battery connected in parallel to a capacitor and to a resistor, right? The positive terminal of the battery is connected to the top lead of the capacitor, the top lead of the resistor. The bottom terminal of the battery is connected to the other side of the capacitor and to the other side of the resistor. So let's see if there's any other ones that are like that. Okay, so is B like that? Well, okay, let's look. The top is connected to both the positive, the same, or one terminal of the capacitor and one terminal of the resistor. The bottom is connected to the other side of the resistor and the other side of the capacitor. So yes, this is the same circuit. So A and B are the same. Okay, so I screwed up again. I got to fix that. It's B and A are the same so far. Okay, let's look at C. Is C the same? Well, positive terminal of the battery is connected directly to the resistor as it is with A and B, but it's not directly connected to the capacitor, right? Here's the positive terminal. It's the negative, the other side of the resistor is connected to the capacitor. So this is not the same circuit. It's not the same wiring, because both of these circuits, A and B, have the positive terminal directly connected to one side of both the capacitor and the resistor, and they both have the negative terminal connected directly to the other side of the capacitor and to the other side of the resistor. So this C is not the same circuit. So C is wrong. So this should be B. Let's look at D. Okay, this is a weird looking diagram. There's really, other than confusing people, there's no point in drawing it like this. But let's look at this one. Okay, here's the positive terminal of the battery. It's connected by a wire directly to one end of the resistor, and it's connected directly by another wire to the one end of the capacitor. Okay, so far so good. What about the negative terminal of the battery? Well, that's connected directly by a wire to the other end of the resistor, and it's connected directly by another wire to the other end of the capacitor. So as weird as this drawing is, it does correspond to the same physical circuit, the same wiring as A and B. So the answer here, I've got to fix the typo, is A, B, and D all represent the same circuit. Okay. So there's different ways you can draw these circuits. You know, A, B, and D are all different drawings, but they're all the same physical circuit. Okay. Neither one is any better than the other. In this course, we're going to probably draw it as A because I think it's much easier conceptually for you to visualize this wiring and the configuration of A versus B and D. So you can draw them however you want, but it's easiest to analyze the circuit, at least in my opinion, using the drawing in A. So we're going to stick to these type of drawings here. So the next step that we're going to do is we're going to learn a few basic techniques for analyzing DC circuits, okay? When we say analyzing, what we mean, at least in the next couple chapters, our primary objective is to A, calculate the current through every component in the circuit, and then B, calculate the potential difference across each component. And in addition to helping us understand the circuit as a whole, if we know the current through each component and we know the potential difference across each component, then we'll see in the next section that we can calculate other parameters such as the power consumed by each component, and there's other quantities we can calculate as well. But once we calculate the current through each component and the potential difference across each, we have all the information we need to really study the circuit. And so that's what we're trying to do. So we need a couple techniques to be able to do that, and we've already introduced these, but briefly in the previous chapters. The first technique that we've learned is what's called Kirchhoff's loop rule. And we're going to go over these in the next few slides again, so don't worry if you forgot them. Kirchhoff's voltage law, or Kirchhoff's loop law, that the sum of the potential differences around the loop is always zero. Then last chapter we did Kirchhoff's current law, which just says that the sum of the currents into a junction must equal the sum of the currents out. And then the third one is Ohm's law, which just says that the potential difference across any resistor is delta V is equal to I times R. Should be a capital I. So let's quickly review each of these, and then we're going to apply it to analyze a simple circuit. Okay. So Kirchhoff's voltage law, remember, just says that if we go around the loop and we add up all the potential differences across each of the components, they all have to add up to be zero, right? So in this particular case, suppose we start right here in the upper left, and we can pick a direction. So let's just go clockwise, okay? And we find the potential difference, delta V1, across the first component. We find the second one, delta V2, the third one, delta V3, the fourth one, delta V4. Kirchhoff's voltage law, or the loop law, as your author refers to it, says that all of these potential differences must add up to be zero. Okay, well, we know that each one is not individually zero, or you don't have a very useful circuit, right? If they're all zero, it means no current flows. So what this means is that some of these have to be positive and some of these have to be negative. And this is where the sign convention, it becomes important, okay? So positive values of delta V means that the potential energy, or the potential, increases if we go across the component. And so those will be positive numbers. And negative values, like for example, going from a negative terminal to a positive terminal of a battery, okay? So that means that the potential difference as we go across the battery increases. We're gaining potential energy. Negative values are typically across resistors and other components where potential energy is lost as we go across them. And so for these, we'll have that the delta V's will be, which is IR, Ohm's law, are going to be negative. And that's if we go in the direction of current flow. And so Kirchhoff's voltage law says if we add all of these up and we go around the loop and we keep our sign conventions proper, that they should all add up to be zero. So the positives will equal the negatives. Okay, so we'll get to that in a minute. Let's do an example here. Okay, so here we have a pretty basic circuit. We have a battery connected to a resistor, and that's all we have. Here's a positive terminal connecting with a wire that connects it to one end of the resistor, and then the other wire end of the resistor is connected to the negative terminal of the battery. Okay? And if you look at the circuit diagram, this is a single loop, right? In other words, there's only one path for the current. Okay, so let's apply Kirchhoff's voltage law, right? It says that if we take delta V battery, the potential difference across the battery, plus the potential difference across the resistor, Kirchhoff's voltage law, or the loop rule, says that they have to add up to be zero. Okay, so the next step is we have to, we know that the current flows from the positive terminal of the battery through the circuit to the negative, right? Because remember, current is by definition the flow of positive charge, and positive charge will flow from the positive terminal to the negative. Okay, I know. It's really the electrons that are going from negative to positive, but Ben Franklin guessed wrong, and the world lives with it. So the current we take as going from, we know that the current goes from the positive to the negative terminal. So let's draw the circuit diagram, which we did, and then let's start at the negative terminal of the battery. Okay, so in this case, we're going to start at the negative, we're going to go around the loop till we get back to the same point. So the potential difference as we go from negative to positive of the battery is just a plus delta V battery. Okay, now we go through here. There's no voltage lost across the wires, remember, because the wires we're going to assume have zero resistance. And so if it has zero resistance, Ohm's law says we don't lose any voltage across the wire. So we've got delta V battery. Then if we go across the resistor in the direction of current flow, the voltage difference is IR, but it's negative, right? We're losing voltage as we go from the side of the resistor closest to the positive terminal to the side negative. So in other words, if we go in the direction of current flow, the voltage difference across the resistor is negative IR. So we add these up and we get delta V battery plus a negative IR is 0, and that just means that delta V battery is IR. Okay. In other words, the voltage produced, the potential difference across the battery, which is produced by this chemical reaction, this potential difference is lost in going through the resistor. So this is a user of power, and this is a generator of power. Okay, so this is just applying Kirchhoff's voltage law. And so if we pick the direction of the current, we choose to go around the loop in that direction, which we always should do in the course. That means that this delta V across any resistor is negative IR. See? Second one, this law is super easy. Kirchhoff's current law, right? That just, remember all that means is it comes from conservation of charge, right? So here current is the flow of charge, and you get to a junction. And since charge by nature cannot be created or destroyed, it can't really pile up or disappear at any junction. So in other words, what comes in, like water flow, if this is pipes, what comes in must go out. And so the current coming into a junction, the sum of the currents in must also always equal the sum of the currents out. So here's one example where you have one current coming in and two out. Here's another one where you have two currents coming in and one current coming out. So you can think of this like a T of a pipe and water. But the sum coming in of the currents must always equal the sum leaving, okay? And what that means, if you look at this series circuit here, is if you don't have any junction, so this is a series circuit, right? One loop, everything daisy chained one after the other. That's a series circuit. They're connected in series. What this means, since there are no junctions, is that the current must be everywhere the same in this circuit. In other words, otherwise charge would pile up. If there's more current at this point than at this point, it would come in faster than it can leave, and the charge would pile up. And so one consequence of this is that if you only have one loop in your circuit, that the current has to be the same everywhere. And so if these were 4 light bulbs, and they were identical, they would all glow equally bright because they all have the same current going through it. So the current does not get used up by the first element. They all get the same current. Okay. So that takes a little time to get used to. Here's a numerical example. So here's the battery, and let's suppose you have 10 amps of current, and that's coming into this junction here, and 10 amps in means you must have 10 amps out of the junction. So you have 7 going this way and 3 going this way. 3 plus 7 equals 10. Whatever comes in must come out. Okay. Now we have them merging again. Here's another junction. 7 plus 3 coming into this junction equals 10, and you must have 10 coming out. And so you have 10 amps going back to the negative, which is reassuring because you must start and end with the same amount. So Kirchhoff's current law is pretty easy, right? It just says whatever comes in must come out. Then the third rule that we're going to use in our circuit analysis is what we learned is Ohm's law, and we learned that in the previous chapter. And that just says that the potential difference across any resistor is IR, okay? Now we'll have to, we tack a negative on when we're doing our circuit analysis, but the magnitude is just I times R, okay? And remember that this only works for circuits for components like resistors, batteries, and wires, where the relationship between current and potential difference is a straight line, okay? It does not work with other components like diodes and semiconductors, like transistors, and a lot of these chips, these IC chips. Those Ohm's law does not work. So in this course, we're going to assume that wires have no resistance. Okay, really, they have a little. So if R equals 0, we don't lose any voltage across a battery. So the voltage difference across any wire, by a wire I mean, is 0. So the only component that we're really going to be using Ohm's law for primarily, not always, but mostly, is for resistors, okay? So let's apply next step. In the next slide, we're going to apply this in our first example of a circuit here. But remember again, the main goal of this is we want to calculate the current through any each element and the potential difference across it. Okay, so here we have our first circuit that we're going to analyze. All right, so we have a 50-volt power supply. Remember, that's how we draw the battery. The battery is drawn as 4 lines, and that's connected to a 40-ohm resistor, and then to a 60-ohm resistor, and then back to the negative terminal of the battery. And it's a single loop. So in other words, this is what's called a series circuit. Series means one after the other in a single loop. So you have a 40-ohm resistor and a 60-ohm resistor connected in series with a battery. Okay. So before we start crunching here, we're going to notice a couple things. Okay, since there's only a single loop, there's only a single path for the current to flow, that means the current must be the same everywhere in the circuit. So in other words, the current through the 40-ohm resistor must be the same as the current through the 60-ohm. So in series circuits or through any single loop, the current has to be the same everywhere. The charge does not pile up anywhere. Okay, so that's the first thing. And so there's only one current in the circuit, and we need to find that current. It's the same for everybody. Now the second rule, remember, we're going to apply Kirchhoff's loop law, the Kirchhoff's voltage law. We can start anywhere we want. So I'm going to choose to start at the negative terminal, and I choose to go counterclockwise, okay, around the loop. And we're going to add up all the potential differences, and they have to be 0 by Kirchhoff's loop law, the voltage law. Okay? So what this means, we know that the current flows from the positive terminal through the circuit, through the wire, and back to the negative terminal. So we know that the current flows counterclockwise in this circuit. Okay? So if we know the direction that the current flows, we almost always, or it's easiest, if we just start going around the loop in that direction of the current flow. So example, we're going to go around the loop counterclockwise because we know the current really does go counterclockwise from positive to negative of the battery. Now, in other circuits, they may be more complicated, and we may not know which direction the current flows, okay? No fear here. We guess a direction, okay? So, for example, in this case, suppose we don't know that the current flows from counterclockwise, but we draw it as counterclockwise. We guess, okay? So let's just guess it goes counterclockwise. We'll find out at the end whether we're right or wrong by the sign of the actual current that we calculate using the analysis. Uh, so let's just suppose, for example, that in this case, we assume the current flows counterclockwise. We calculate current and we get negative 2.5 amps. Okay, the negative sign tells us that our guess as far as direction was wrong. Okay, we guessed counterclockwise. We get a negative number. What it really means is that the current is really going clockwise around the loop. Okay, so in other words, we've got the we're always going to calculate the right magnitude, but this, if you get a positive sign, it means that the actual current is in the direction that you drew it as, in this case counterclockwise. If you get a negative value, it means, oops, guess the current's going clockwise. Okay, so that's what a negative value of current means. Okay, and it's just like when you're in lab and you hook up a voltmeter or an ammeter to measure current or voltage, and you get a negative value. It just means you hooked your leads up backwards. Okay, the magnitude is right. So that's what the negative value of current tells us. So don't panic. If you ever don't know which direction the current flows, if it's not obvious, just pick a direction, draw it as that way, like counterclockwise, and if you get a negative value, it means you guessed wrong and the current is really in the other direction. Okay, so enough of my babble. Let's move on and let's analyze this. So what we want to do is we want to calculate the current in the circuit, and let's remember the same current for both because there's only a single loop. And once we know the current, we can use Ohm's law. Delta V is equal to IR. If we know I and we know R, we can get the potential differences, delta V, across each of the resistors. Okay, so here we go. We're going to start at the negative terminal of the battery, and we're going to go counterclockwise, okay, because we know the current flows counterclockwise here, from positive to negative. So we get the first potential difference, delta V battery, plus delta V across the 40 ohm resistor, plus delta V across the 60 ohm resistor. That always has to be 0. Adding them all up, they all have to add up to be 0. Okay, so that's the first step, always, for any loop. Okay, now what are the delta V's? Okay, well, delta V battery is plus 50 volts because we're going from negative to positive, so we're gaining 50 volts of potential. So delta V battery is going to be a positive number. Now we go across, here we go, we go across the 40 ohm resistor. Potential difference is IR. We're going in the direction of current, so it's a negative IR, so it's negative. Okay, now we go through here. 60 ohm resistor. We're going in the direction of current. Delta V here is just 60 ohms times I. And in this, it's a negative value because we're going in the direction of current. In other words, we're going from more positive potential on this side to less positive potential on this side, and so the change in potential is negative. Similarly here, we're getting closer to the negative terminal, so we know that we're more positive on this first side of the resistor, and we're less positive on the second side because we're going from the positive toward the negative. And so delta V is going to be a negative number. We're going to lose potential going across this resistor. And when we get back to the end, the charge gets back here, completely exhausted and panting, that whatever it gained in potential going across the battery must have been lost in going through the two resistors. Conservation of energy. You have to start and end at the same energy potential. You can't gain or lose going around the loop. Okay, so let's do that. So we get delta V battery minus I times the 40 ohms minus I times R 60 ohms is 0. Okay, Now you might say, well, how stupid. Why don't you just put in 40 ohms and 60 ohms? True. But I want to keep it in symbolic form just right now because this applies for pretty much any case, okay? Um, so let's do that. So now we know that the resistor values are 40 ohm and 60 ohm. We know that the potential difference across the battery is 50. We know everything but the current, and so we can solve for the current. And so we solve this, and we get I is equal to the battery voltage divided by the sum of the resistors. There should be a space here, okay? This is not times delta V battery. We can plug in 50 volts is equal to delta V battery. 40 ohms plus 60 ohms, the sum of the resistances is 100 ohms. And we get I is equal to 1/2 amp. Let me fix this. So I is equal to the battery voltage divided by 100 ohms is equal to 0.5 amps. So I screwed this one up. Ignore this delta V battery here. I need to get rid of it. Now that we know the current, we can find the potential difference across each resistor using Ohm's law. And so for the 40 ohm resistor, we have I as 1/2 amp as the current. 40 ohms is the resistor. The voltage dropped across this 40 ohm resistor. We lose 20 volts in going across it. Okay. 60 ohm resistor, the potential difference is I, which is 1/2 amp, times 60 ohms, and that's 30 volts. So in other words, we lose 20 volts across the 40 ohm resistor, we lose 30 volts across the 60 ohm resistor. Okay, so now we've found all of the currents, and there's only one current. We found all the potential differences. We're done, right? No, almost. Let's check our answer here, okay? So we know that the sum of the voltages has to be 0 around the loop. So 50 volts gained in going across the battery, 20 volts lost in going across the resistor, 30 volts lost going across here. We gain 50 here, we lose a total of 50 here. And so the sum of the potential differences gained in going across the battery must be equal to the sum lost in going across the resistor. Or algebraically, they all have to add up to be 0, right? 50 plus a negative 20, because we're losing 20, plus a negative 30 is 0, okay? So on this thing right here where we're using Ohm's law, we're calculating the magnitudes, okay, of these voltage drops. And so at the end, remember always to add up the gains and the losses. We gain 50, we lose 20, we lose 30. And whatever you gain must be equal to whatever you lost, because you have to start and end back at the same voltage. You have the same point. And so this in general is a technique that we're going to be using. We start off always with the loop rule, or usually. We typically use that to get the current. Once we know the current, we can calculate the voltage drops across the resistors. So this is our first example of actually analyzing a circuit. Next time we're going to get into power calculations and then slightly more complicated circuits. So we will see you tomorrow.